Hey, how are you? And welcome to last week we have for the manufacturing engineering lab sessions. In today's session, I'm going to complete what I postponed in the past 2 weeks because we were finalizing the pump work and also we did the testing last week. Today we're going to do the part number 3 and 4 together for the major project discussion. So what I'm going to start with is talk about the pump, and then we're going to have the 2 slides, and also again take you around the lab to show you some of the machines which are required to do the work to finalize the pump shape after we did the casting for the main body. I think that we already talked about the making of the shaft, so we don't have to repeat it today. Mainly it's going to be done on the turning machine at the beginning to cut it to 3 stages. Well, let me get an example. Okay, so we're going to make it as on the turning machine first to cut it into multi-stages, and we're going to do the same thing for the other side. We got the operation number 2 until we're going to have the 4 parts to be cut it on the shaft. Later we're going to hold it by using the holes we had on both ends on the milling machine once again, and we're going to do what we call the turning, this will be called the holding between the centers, and then we're going to do the cutting of the gear by using the gear cutter. We have something called the gear cutter. We need to use the indexing tool to divide the circle into unequal divisions and cut the gear teeth. The same thing we'll be having for the supplying. I think I showed you that the tool is called the Dave Tell, and once again I will put the photo here just a little bit, show you how many numbers of the division we will need to set on the indexing tool. I'll show you a video for that, and we set that to reduce the time of the machining. We can have what we call the CNC milling center, which is going to be a machine which can do both the turning and the milling at the same time, and this will reduce time. Sometimes this can have multiple spindles, so this can reduce the time for the working or the turning and the milling machine at the same time. Later we need to hold the part once again, but between the centers we're going to turn it. We're going to get the grinding wheel to have this good surface finishing on the sides. Also a special grinding operation should be done for the teeth to achieve the good surface finishing between the mating gears. Otherwise we're going to have the stuck of the gears, and this will reduce the efficiency, and also is going to stop the pump sometimes from working or starting. Now the next step was for the week number 4 is going to be about the making of the main body of the pump. Now the main body, if you're going to inspect the surface, I can assure you that this one has been made by what we call the sand casting operation. The material we're using here is going to be gray cast iron. Mainly this was what we are going to have, or ductile iron material. The density, you can find this one online, and well, actually it's not going to be very important now. So you can say that ductile iron is going to be the alternative material. The gray cast iron is going to be the main material you're going to use. The process of making that is going to be done by the sand casting. When you're going to do the sand casting, you're going to make the whole block shape as a pattern, and this whole this part is going to have the solid part. So we're going to use that to make the cavity inside the mold, which is made of the sand, and then we're going to add some cores to provide the pre-initial shape of this gap and the holes in the back. Just remember that this course could be made of one part, and this will make it much easier to be held inside the cavity of the mold, and also it's going to be much easier to be removed. At the same time, if you can see here that actually we can see the other side, we can see the other side of the port from here. That means that this core we're going to have should be one part. And of course, the core we said is going to be made from the fired sand that can hold the high temperature, and then we can break it or remove by the vibration after we get to achieve the solidification state of the cassette part. Now, the next thing we are going to show you is the machining process for this part. So, hey guys, how are you? Well, I'm talking about the part number 4, and well, you can join me. I'm recording that, and we're going to share it with you anyway. So let's try to share the screen from now. Okay. Oh. Okay, so once again, just to repeat what we just said, we said that in the previous session, we discussed about how to make the shaft. We said the shaft is going to be done by having the bar, cut this bar on the milling machine, turning machine first, so multiple steps. And the same thing is going to be for the operation number 2. We said we can accelerate that by doing the work on the 20 spindle turning milling machine. As long as it's going to be turning milling machine, so that's mean that the spindle itself is going to have the indexing tool, which can be programmed, and we can divide the circle into a multiple stage, and then we can cut the gears and the supply at the same time, and then we are going to get the part finished. We only need to take it once again to the grinding machine to do the grinding process for the side to have the good surface finishing here, and also we need to do some grinding for the gear teeth, because we said this will be a critical dimension. We should have very good tolerance between the gear teeth when they're mating, otherwise we're going to have either an efficiency loss if they're going to have big gap, and we're going to have close tolerance between them, and this will hold the part due to the high fraction. We're going to have bad surface finishing or very close tolerance between the dimensions. So this will be a very critical dimension. This will be a very critical dimension because this will sit inside the pushes and should be rotated at a very high velocity, so we should achieve that. Also the diameter of the gears, because they're going to be in contact with the walls, it should have very high tolerance in the dimension. So the next stage was and that's what we're going to finish today, is how to make the main body. We said that the main body is going to be made from the ductile iron or the gray cast iron. So you have 2 options. Mainly is going to be done by the sand casting operation. So the pattern we are going to use is going to be exactly similar to that shape, but it's going to be solid. It's not going to be hollow. The pattern should be solid. We're going to make the cavity inside the 2 halves of the mold, and then we're going to use the core to generate the 3 cavities we're going to have here. So having these cavities is going to give us 2 most important things. First, we're going to save the material we're going to remove later, because we only need to do the boring for these diameters, and thus we're going to save the amount of the energy and the amount of the wasted material we're going to remove. In addition, you can see that actually from here we have a direct access to the port. So this will simply going to create this connection between the cavity of the gear pump and the port itself. So once again, this will reduce the time for the machining, and of course the complexity of the machining, because this height of the inlet is going to be quite long, and this requires a special machine to do the work. After we achieve the solidification for the cassette part, we can remove the core, and we said that the core is actually going to be made of the dry fired sand to be a little bit hard, and I prefer to have it as one part. So it's going to be something like the big shape of this cavity here, which is going to have the 2 extensions for the 2 ports, one part, so it's going to be much easier to be held inside the cavity, and also it's going to be much easier to achieve the required shape internally. We got the part. Of course, the surface finishing for the cavity is going to be too bad. The dimension is not going to be accurate. And we would like to have the good surface finishing, the accurate dimensions, and the way to do that is by doing the boring operation. So first we're going to take the part after we do the solidification process to the milling machine. If you take a look there, I put one of the pumps with, well, I again to bring the, I can take the computer to that just to show the screen what I'm talking about. Okay. So that's an example of the milling machine. You can see that I added the tool, which is the face miller, and by the moving of the part below the cutting tool, we're going to achieve the flat surface finishing there. Even the holes, we can have the head of the drilling to be sitting on the milling machine itself. And of course, this is not CNC milling machine, this is manual one, but it can do the job, still can do the job. So just moving the table to the Y direction and the X direction, and this will cover the whole surface of the top, and then we can flip the part, do the same thing from the other side. The same milling machine also can be used to have a tool which is going to have a multiple stage. Well, to give you an example of the multiple stage cutting tool, let's say it's going to be a shank, which is going to be made of the carbon fiber carbons and carbon fiber, sorry, and maybe it's going to have the same shape like that, or at least the same stage. We're going to have the cutting tool at every stage. So when I'm going to rotate the cutting tool and insert it inside the cavity, by the rotation, this cutting tool will expand this diameter, and the smaller one is going to do the same for the lower one, and then we get to reach the end, they're going to do the face milling for the surfaces. So we're going to have the multi-stage boring operation. So boring here, face milling on this level, the lower one, and the same thing is going to be happen to the side where we're going to insert the bushes, and this once again going to be a critical dimension. So we did the face milling, we do the internal boring, and then we are going to do the drilling and the tapping for the holes that are going to help the threaded heads like that. Okay, so we're going to do 6 holes drilling, 1, 2, 3, 4, 5, 6 drilling, and then tapping. The tapping is going to use a tool which is going to have the same thread we're going to have here. Okay, so we can fix these threaded heads. And also we're going to have 2 holes which are going to have very critical dimensions that are going to help the dowels. The dowels need to be inserted by some fit press. So we're going to have some pressure to fix them in, and they are going to be stable there. We can take them out by mechanical method, but we're going to damage the good surface finishing of the dowel. Now the dowel is going to be a critical issue because the location and the dimension is going to be very high accurate, and we need to do it by the drilling first, then we need to do some expansion for the diameter by using the reaming operation. So the reamer is going to have the straight lines and is going to increase the diameter by a fraction of millimeter to have it very accurate. In addition, is going to have very good surface finishing. Now we finish with the first phase. We're going to take the part to the second phase. We're going to repeat the same operation by doing the face milling here, and then we're going to do the internal threading by using the milling machine. To show you a video on how to use the milling machine to do the internal threading for the poles, I may prepare the video here. Where is the video? Yep. Okay, so the first video is going to be on how to make the internal thread. I'm going to go back once again. Well, actually, you can take the name of this. And you can see in this example, not going to be exactly what I'm looking for, but still, it's how to do the boring operation to expand the diameter. So we can talk about the boring head. Which one is going to be short this video? All the videos are quite long. Boring video on the CNC milling machine. So we will try to watch just a little bit of this video. At least we're going to have the.
A small thing can make a big difference. See this here? That is what makes the difference between having the capability to ramp with.
Wow, that's really boring. Get it? Because it's a boring video. Hi, I'm Stuart McConaughey, and today I'm going to show you how to bore this 6AL4V titanium.
It's about to get crazy. It's about to go down.
Boring these beautiful 1-inch holes that have a tolerance of ±5/10 in this rocket part made out of 6AL4V titanium. And I get to show you this awesome Kennametal boring head that you can control all the way to 80 millionths of an inch. All right, so today I'm gonna show you how to set up a boring head. First, maximum diameter is 1 inch and 53 thou. We're gonna bore, and I'll be roughly at 1 inch. Perfect size.
Okay, so I will keep that. Have So let's go back to the camera, I think. Yep, okay, now we talked about that. Yeah, well, the same operation is going to be repeated to making the cap. Once again, this will be casted, and then we're going to do some face milling. The drilling, this will be at 4 holes in that case, and this should be at the same location of the one we had on the main body. Otherwise, you're going to be able to fit the threaded parts at the same time.
I was just wondering, do we need to make a CAD model of this or just the program?
Well, I think that we already have some CAD models available for you on the canvas. You can use them.
Okay.
Yeah. But if you would like to take some photos and use it, it's not going to be the issue. Yeah. Okay, so just remember that these holes are through holes. The diameter is going to be larger than the one we had on the main body because you can see that we're going to have the free movement of the threaded parts within. Same thing, we're going to have the dowel, and these dowels holes should be opposite and at the same location compatible with the main body. We are going to do the cut for the what we call the slot here. This slot is going to accommodate the lip seal, which is going to prevent the leaking of the oil under higher pressure. Yep, and also we need to do some boring here, and then we need to do some yeah, I think the boring is going to give you the good service finishing. Now the same operation I will repeat here once again. Face milling, again to cut the slot and the drilling of the through holes, and done for the main body. So in the next slide, we are going to check the operations again, and we're going to show what are the critical points we are going to have for this pump. This will be the main body. Actually, I should do that 2 weeks ago, but once again, I said that we were busy with making and testing of the pump. So to do the work on the milling machine, you need to hold the part. Otherwise, it's going to push due to the force of the cutting we're going to have for the cutting tools. And to do that, we use something called the clamp. So you can see that's the clamp, which hold the part on the table. Then we can do the cutting. The clamp usually is going to be holding the part from the top, and this is not going to be suitable if we are going to do the face milling. So the other way to do it is just using the vise, like the one we use on the drilling machine, the vise which is going to hold the part from the side, then we can do the work freely on the top and internally. In this operation, you can see that we are going to have a special clamping, which can hold multiple parts at the same time. And this is what we are going to use in CNC milling machining center, which can do multiple parts at the same time. So you can see that these are the clamps. Again, the clamps is holding the part from the top, and this will be good if we're going to do some internal cutting here. But we're not going to be able to do any face milling because we're going to hit the clamp themselves. Maybe this will be useful if we're going to do the work on this side, because we only get to limit the work on this area, but it's not going to be useful again to do it for the face milling on the top face. Usually all the clamps are now automated to increase the time, to increase the efficiency for the work. So they're going to be moved by using the pneumatic pressure we're getting from the cylinder. So even the robotic arm now can handle the part, the work. It doesn't need any interference from the human to tighten up or removing the part. Different shapes of the clamping, as you can see here. And as I told you that most of this clamping not going to be useful for the face milling or the top surface, because if I get to clamp it, okay, let me show you that in the video. If I get to clamp it, that's mean I'm going to have the clamps at the top here. This is not going to enable me to do the face milling. So we always going to hold this part by using the vise from this side, and then we can do the work freely. Okay, anyway, you will talk about that in your report. I think this is work on an example. Okay. Now you can see here, this will be the boring operation. You can see here that we're holding multiple parts at the same time, and this will increase the efficiency of the work because we are going to reduce the setup time. Now I do the setup for 2 times 4. As we have 8 on each side, so total I get 16 parts to be machined in a single setup. Once again, this machine is called the machining center. It can do most of the operation at the same time. Now this will be the reaming operation of the boring to the dimension, and we can do some test will be the turning operation. The drilling operation, and this will be the tapping operation to make the internal thread for the drill holes. Okay, and of course we can set it to the other side on another machine and do the same thing. So that's what we call the CNC machining center. It's usually going to be turning milling operation at the same time, and but for this one specifically, this will be mainly a milling operation, because I can tell that we have a table here, and this table is going to have accommodate many of the setup we just saw earlier, which can hold multiple parts. Usually we're going to connect that to a conveyor belt. The conveyor belt is going to feed the setup one after the other, and this will reduce the time for the stopping and the setup for the part inside the machine. That's what we call the multiple pallets. So you can see that every pallet can have a setup on them, or 2 setup. So while the first one is going to be under the processing, we can load the second one, and then when the first one is finishing, the thing will be shifted, We're going to start to unload the first one and load it with the new material while the machining is happening to the second one, and so on. Is that video? Now, this will be for the pellet changer. So instead of having the sliding, this can work on a conveyor belt as we mentioned, and we can do the operation at faster rate. Now you can see that will be the operation. This will have 6 stations of the pellet pools, and this, of course, going to take us, give us more time for the loading and unloading while the machining is still running on the other pallets.
The EC400 pallet pool
I'm
is a
not
powerful
sure
machine tool for both job shops and high production environments. The high output horizontal machining center with 6 pallets, the EC400 pallet pool is easily incorporated into a production shop's lineup. The machine's minimal investment cost, easy one-day installation, and user-friendly intuitive pallet programming system make the EC400 pallet pool a low-risk option for job shops looking to automate their processes.
So of course, we're going to have the
Like other high-productivity machines from Haas, the EC400 pallet pool has a number of unique features that make it a perfect fit for both high-production environments and job shops looking to expand their capabilities. Unique features: a 70-pocket side-mount tool changer, automatic chip conveyor, 300 psi through-spindle coolant, and advanced tool management functions make the EC400.
Again, to continue with that. Okay, now once again, we said that the work is going to be done first to do the face milling for the started face, which is going to be top face. And this will be done by doing the milling operation by using the face milling cutter. The face milling cutter, well, later with the same setup, we can do the drilling and the threading of the threaded holes. And we can do the drilling and the reaming for the dowel holes. Now, dowel holes, once again, we said it should have a clearance fit. Clearance fit, that means we can push the dowels inside with using the minimum force. So we can remove them later if required. Okay, once again, it's going to be inserted by doing the press fit. The other two work we're going to do with the same setup is going to be the expansion of the size for the gear and the push bore, and this will be done by the boring operation. We said that we can use either the normal boring operation or we can do the multi-stage cutting tool to reduce the time of the machining. We mentioned that. Okay. Then we can turn the part to the other side in the second setup to do the work on the inlet and the outlet ports. So first we are going to do the face milling for these two faces, and later we can do the internal thread by using the milling machine operation. So for the started face, we are going to use the mill started face operation description as the operation number 1. On this table, you can do the table similar. We can use the face milling cutter. This will be an example for the face milling cutter, and as you can see, that the cutter itself is going to hold a multiple cutting teeth, which is going to increase the efficiency of the cutting operation. Usually in the face milling cutter, more cutting teeth is going to increase the rate of the removal of the material. So that's how it's going to work. Just simply rotate, passing it through the face, and it's going to remove a layer. So the tool in this photo is the 160 50.8. The insert, we're going to have the golden one. It's going to be the SEKN 1203. Okay, so these are some specifications of the cutting tool, and you can use the K20 as the insert grade, and the cutting speed recommended for this operation is going to be 120 meters per minute, and we can add some supplier, imaginary supplier for this cutting tool. The next step is going to be the drill cap screw holes. This will be the operation of the face milling in slow motion. So you can see that in the case of the face milling is going to be discontinuous operation. When we say discontinuous operation, you can see that we can see that the blue part we have here is what we call the clamp, which holding the part with the uh, both sides. Again, we said that we can do the boring and the face milling operation for the gear and the bush bores by using either the normal cutting tool, which can do the boring, like the one we saw in the machining center operation, or we can do a custom multi-bore and facing tool to reduce the time. So once again, you can see that the tool in this photo is going to have the multiple diameter. The small diameter is going to be the same size of the push bores, and the larger one is going to be the same size of the gear bore. We said that these parts, these bores already has been created by using the core we inserted inside the casting hole, and we only going to expand it to the dimension. So this operation can be done in a single step. We are going to take it down and take it up, and then the face has been generated. We can repeat on both bores. So the description is going to be the rough bore here and the push bore. The tool is going to be custom multi-bores and the facing tool. We need to define the insert and the insert grade. You can use the same one we had in the previous example, or we can choose a new one. So you can see here that the tool is going to be the TMG, the grade insert of the KM3015, and the cutting speed is going to be 140 per minute. Okay, so first we are going to do the rough operation. As you remember, the rough operation, we're going to add lower RPM value, and we're going to insert it at higher feed rate. So it's going to rotate at low RPM value, but the feed rate, which is the vertical movement, is going to be at higher rate. Then the next step, we need to do the finishing operation. So in that case, we're going to rotate the cutting tool at higher speed, but the feed rate, the vertical insert, is going to be at lower velocity to achieve the good surface finishing. I think this will be just a short video to show you how does the multi-step boring tools is going to work. So you can see that the step we're going to have here is where we're going to have the inserts. So we can have here the one we just insert is going to be the internal one. The other stage is going to be for the face milling, and the third one is going to be for the outside turning operation. So we did the multiple stage at the same time. So the stage we have here once again is this one, this stage number one. This will be the stage number two. We do the face milling and we do the external boring. So we use 4 insert to achieve the goal. Okay, and we saw how we are going to do the work on the other face. Now I have some videos here which are going to be very useful actually for show you what we're doing. I think that we saw this video, we saw this face milling, the gear hopping and the supplying hopping. I think this will be useful.
On this H13, I will machine a 24, 48, 44 tooth exterior spline. I am using our 8-flute replaceable insert shell mill. The size of the shaft is 1 inch, 880. I will rough, then do a finish pass. Roughing will be at 921 surface feet. My RPM is 1,600, and with a chip load of 4,7/10 per flute, I will be machining at 60 inches per minute. The finish pass will be at 2,500 surface feet. My RPM is 4,500, and with a chip load of 8/10 per flute, I will be machining at 30 inches per minute. The approximate cycle time is...
Okay, now this cutting tool is called the hopping. do the hopping, so it's going to rotate, and then generally the cutting on the shaft was going to rotate at the same time. And it's going to result by having the supply. Actually, there's another operation which can do the gear cutting at the same time instead of using the tool for the
3 minutes.
gear. Okay, so what next?
Foundation. Being the first enterprise that developed a skiving process technology in Taiwan, we have always taken to improving technology and innovating equipment as our core concept, microgear, and have passed the ISO 9001 international quality attestations, this being a most important enterprise partner. Process techniques and process. Procurement of raw materials. Incoming raw materials must pass RoHS and relevant quality and safety standards and be certified by our QC department before further processing. Once the raw material passes the QC standards, it is then put through CNC machining to achieve pre-shaping. The entire process is done by auto-feed CNC equipment to ensure high productivity and precision finished products. Vernier height gauge, run-out inspection machine, etc. are used to check the length and concentricity of the finished product. The purpose of knurling is to improve the shaft in the way of being firmly fixed on coiled silicon steel sheet. Quality control personnel then inspect the outside diameter. Advanced equipment imported from Europe and the U.S. is our best auxiliary to achieve excellent quality standards and production efficiency. As an example, the Swiss-made Gleason Fowder P60 is used for rolling the motor gear shaft and skiving the shaft. A U.S.-made Phoenix 125GH by Gleason is used for machining automotive gears. Chow Cha is also a pioneer in introducing the Kofer MZ130 for the hobbying and skiving of microgear, as well as the machining of the motor gear shaft, bevel gear, worm, and worm gear. Several Kofer 200s have been imported to meet the increased hobbying and skiving demands in gear and motor gear shafts. Chow Chow will keep apace with the market trend and customer demands in order to be the provider of choice. The skiving process is applied to gear and shaft to correct heat treatment-induced deviation, hence reducing noise while increasing lifetime. The tooth lead and tooth profile of the skiving process products are then inspected by a specialized inspection machine to ensure the quality of the finish.
We said that this will be a good.
Gear lapping is a surface treatment of the gear and a common way to increase gear precision. JIS 0 or DIN 4 is attainable by this method.
What Jesse mentioned now.
In addition to the state-of-the-art inspection equipment used to carry out computerized inspection of gear profile, gear lead, and pitch, QC personnel routinely sample the tangent length, root diameter, topping, and outside diameter. We also provide heat treatments such as carburization, high-frequency hardening, and nitrification to harden the surface. Heat-treated final products will then go through slice sampling and embedding inspection to ensure the correctness of the hardened depth and stability. The precision grinding of the shaft to increase its roundness. And then a full inspection of our final products in terms of the outward appearance and outside diameter. To further increase the product quality, automatic ultrasonic cleaner is used for cleaning and drying to prevent rust caused by residual moisture on the final product. It is then packaged to ensure the integrity of the product during shipment. Finally, the product is shipped to the customer designated location, accompanied by a complete shipping and inspection report. Product series. Pinions. Shafts, skiving. Shafts. Cranks. Gear rows and grinding gears. Bevel gears.
Actually, that's a list of their products.
Worms and worm
That
wheels.
we need to cover all that. So what we learned from this video,
Worms and worm.
the operation and how to do the inspection, because you'll need to write down a part about the inspection. Well, that's the inspection for the shaft and the gears. How to do the inspection for the main body? Now you remember that we talked about the engine block earlier and how to do the inspection for it. I casted this part and I would like to do the inspection for it. So the first thing, again, to take a look for the thing visually, and I will see that if all the cavity has been covered, that's done. Okay, so the step number 1 has been done. The other thing, I can do some tests for the part itself. Sometime, if I get to have some internal cavities due to the, for example, part of the mold has been fell down, which is sand, is going to be built in inside. So I can check that, not me, of course, the expert. They get the hammer and start to knock on the thing to check what is the solubility of the part. More advanced method is to take the X-ray, and they will find out if we are going to have some impurities inside. Also, when you're going to do the face filling, if you're going to have some bubbles has been trapped, you will see these bubbles. and that's means that this part is failed, you cannot use it. The other thing is that the last inspection for the whole thing is you can do multiple inspection. The first one is I can put the cap on the part, plug all the outlets, and I'm going to leave one to add some pressure inside the pump. So I will add very high pressure using the water and then lock it under constant pressure. The main body should take the internal pressure to a very high amount. For example, if the pressure I'm going to have here is going to be 360 kilopascal or 60 kilopascal or 30 kilopascal, I always put the pressure with the water, which is going to be doubled, and leave it for example, 3 hours just to check if this part is going to be able to hold the internal pressure without the gears, by the way. I'm going to fill with the water without the gears. Now, why are we using the water, not the oil? Because the water is going to be clean material. So even if things crack, I'm going to have some water on the floor instead of having the oil spilling all around. The final test we're going to do for the pump is I'm going to put everything in, seal, assemble the pump, then we're going to connect it to a machine which is going to do the actual pumping. So for example, if the velocity of this one is going to be 1000 RPM during the operation, I'm going to run it for the 1000 RPM and check how many hours it's going to work. And then I'm going to take the part and check which part has failed. I'll do the operation multiple times. Of course, this will be when you do the research and the quality control operation for a big factory. You're making multiple parts. Then you will find out what will be the weakness point we're always going to have for this pump. Then we can avoid that by changing, for example, the material or changing the manufacturing process. So let's check what the other video we have. Gear manufacturing, because I think that we already have too many things about gear manufacturing.
This factory makes gears that go into transmissions for industry. An automated bandsaw slice carrying a series of carbide tools moves in.
Because of the making of the gear. I uploaded this video already to Teams, which is something old.
Gears are mechanical components used to transmit power and motion through the successive engagement of their peripheral teeth. Gears perform certain key functions within machines and assemblies, such as reversing the direction of rotation or altering the angular orientation of rotary motion. Gears are also used to convert rotary motion into linear motion and vice versa, or to alter gear speed ratios. The methods of machining gears can be classified into two primary categories: gear generating and gear form cutting. Many of the processes used to machine gears may also be used to finish gears. Gear generating involves gear cutting through the relative motion between a rotating cutting tool and the generating motion or rotation of the workpiece. The primary gear generating processes include hobbing and shaping. In hobbing, gear teeth are progressively generated by a series of cuts using a helically fluted cutting tool called a hob.
So this will be
both the hob and the gear blank rotate as the hob is fed axially across the face of the blank. Hobbing is the principal method for producing spur gears and helical gears, and is also used to produce many special gear forms. The main limitation of hobbing is that it can only be used to produce external gears. Hobbing can be performed on a single gear blank, but also allows for the stacking of workpieces to increase production rates. Shaping generates gear teeth by rotating the workpiece in contact with a reciprocating cutter. The reciprocating cutter may be a pinion-shaped cutter, a multi-tooth rack-shaped cutter, or a single-point cutter. The pinion-shaped cutter's axis is parallel to the gear blank and begins cutting by reciprocating while feeding gradually into the blank to a predetermined cutting depth. The cutter and gear blank rotate slowly at the same pitch circle velocity as the cutter enters and exits the cut, incrementally generating the gear teeth. Rack-shaped cutters typically have between 6 to 12 teeth that reciprocate into the gear blank. Once the rack cutter finishes a pass, the cutter is disengaged and returns to a starting point to begin cutting again. When shaping with a single-point cutter, the cutter reciprocates, making successively deeper cuts until a predetermined depth is reached. Gear shapers are used to make internal gears, shoulder gears, and many other gear types that cannot be produced with hobbers. Shapers can also produce non-involute shapes, such as a cam and gear on the same shaft. Gear form cutting typically involves the use of formed tooth cutters that have the desired gear shape or profile. The primary gear form cutting processes include broaching
I sent you an email yesterday.
and milling. Broaching is the fastest method of machining gears and is performed on many different machine types using a multi-tooth cutting tool called a broach. The broach or the gear blank are pushed or pulled relative to each other to remove material. Each tooth on the broach is generally higher than the preceding tooth. As a result, the depth of cut increases with each tooth as the broaching operation progresses. The conventional method of broaching is used mainly to produce internal gears. For external gears, pot broaching is used. Pot broaching is performed on special machine tools having a hollow broaching tool assembly called the pot. Gear blanks are either pushed down, pushed up, or pulled up through the pot to generate the gear teeth. Milling is a machining process that uses the relative motion between a rotating, multi-edge cutter and the workpiece to generate gear shapes. Milled gears are typically produced using cutters that mill each gear tooth space individually. To produce large, coarse pitch internal or external spur, bevel, or helical gears, a process called gashing can be used on heavy-duty milling machines.
That's very important thing because he just keep saying something about the helical gears and the bevel gears. Now, if I'm going to have the teeth coming straight from one side to another, we're going to call the bevel gears. We're going to have it inclined, we call the helical gears. Of course, there's a difference in the performance between both. Usually, the helical gear is going to be better, but the problem is going to rotate at lower speed. The efficiency is going to be higher because the contact area is going to be larger. So the force can be transmitted is going to be higher. But for the velocity term, it's going to be a bad thing. Also, the machining process to cut things helically is going to be more expensive than having this spur gear. You will cover that in the machine design later.
Gashing involves plunging the rotating cutter into a blank for rapid metal removal. After machining, gears may require heat treatment to meet hardness requirements. After heat treating, gears usually require finishing to nullify any distortion that may occur.
So that the grinding machine.
In some cases, gears are machined and finished before heat treatment, and then once processed, surface finished to remove distortion from the heat treatment.
Okay, so let's see what the other video I have. I think we saw this one. Okay, so I think I have another folder which contains the last part for the gear pump, and I think it's going to be a good idea actually if we're going to cover it today. But before that, I think I also have some videos for some of the inspection processes we can have again for the measurement of the gear. And we're going to watch some of these videos now before we're going to go for the slide. That's gear pump. Let me hide. This will be very useful for you to write down the report once again, because you can see that how they do the measurement for the gear teeth and for the shaft, of course, at the same time. So they're using dial gauge. They're moving both, and actually at different position, the dial gauge should be 0. Otherwise, that means that the shaft is not probably aligned. CMM machine, once again, is going to check what the surface roughness and what the dimension and coaxiality for the part. So remember that we use this machine in the lab. We said that this will be the probe. It will check if this part is going to be coaxial or not. It's going to be aligned or having some misalignment due to the cutting. Teeth flank, if dimension, if possible. You can take some photos from this video and add it to your report. I think there are more operations to come. I don't want to spend most of the time. So you can show us every, yeah. That's another thing on how to check. Well, these are the results from the test we just saw. Okay, now that's the test for the main body. Once again, we're going to check the heights, we're going to check the surface softness, the dimensions. Hose diameter, exactly what we did in the lab. We just move it on multiple points and calculate what will be the diameter. Now this gear pump is made from aluminum. It's going to have the ports to be on the side instead of the end. Usually the aluminum one, as we mentioned earlier, is going to have less pressure. It can take less pressure than the one we have, which made of the iron. Okay, next video. The test I told you about, how we can check the pump for the internal pressure. the pump is going to be found from here. The efficiency, the flow rate, the RPM value, all can be found. The pressure as well can be found from this test. Value. This has specification actually, what the material, what the model is. The most important thing that we saw that we have two setup, so we can work on both sides at the same, on two parts at the same time, and this will be a good thing to reduce the time for the machining. One thing you have to remember that we always going to do the grinding operation with an enough amount of the cooling fluid. Otherwise, we're going to burn the surface, and this will damage the meteorological properties of the material we have for the year. Okay, so I think that's it. And the last thing we're going to have is going to be the closing slide. I'm not sure which one is the one. Let's see that. Okay, so now we're going to answer your questions if you have any for the pump. So just remember, the raw materials need to be specified for every different part we have here. You can see that the lip seals are going to be off-shelf item. We don't need to manufacture them. It's going to be made mainly of rubber. The main body is going to be made for the either the cast iron, gray cast iron, or we can use the ductile steel. The shaft is going to be made from the steel, and the truss plate is going to be made from the aluminum by the die casting operation. Casting for the main body. The materials can be the spherical graphite iron or the SG iron, as we mentioned. We're always going to have it as in ingots. We can get the specification from the supplier, and we are going to decide the one according to our need. So you can see here that we have, for example, the tensile strength, our minimum, tensile strength, our minimum value, the elongation, the impact value, the hardness, and the structure. This will be very important to have the good insurance quality. Usually when you get the part, the ingot, you need to do a simple test at home, I mean the factory, before you're going to start to use it. Usually such things should be certified for the supplier. Once again, the casting process, you can use the same flow chart we had from the casting process. I'm going to hide that, so we're going to have a closer look. Okay, so we fabricate the core boxes, we fabricate the pattern, we build the mold, we adding the core if needed, and then we are going to prepare the raw material, melt it, pour it in the casting, solidify, break out the raw casting material, degate and clean the inspection, then we're going to have the finished casting ready. Usually for this part is going to be done by using the green casting method, and the mold should be closed. Then the casting should be ready for the delivery for the client, who's going to be you. Now, why we said it's ready for the delivery to the client, because usually the casting is not going to be done in your workshop. It's need a foundry to do the work. We do some transportation, and this will be a logistic work. The movement through the factory, we can have multiple types of the material handling systems. Do some inspection, check out the dimensions are correct. Once again, we can do the destruction test to check if the quality of the casting is good. If not, just send back everything and ask them to redo it for you. Okay, further inspection, we can use the CMM machine to check the dimensions and the quality of your work. Now we're talking about the driven shaft. Mainly what we worked was on the drive shaft, but the same talk can be repeated directly for the driven shaft without any details you need to add. I think that one of the students asking a question here, just let me check that. No. So who was? Okay. Driven shaft is going to be made, and the drive shaft is going to be made of the bar. So the bars need to be pre-manufactured in the milling factory, and then we are going to select our bar stock. Now we said that the bar stock I'm going to use for our work is going to be the one with the 60 millimeter initial diameter, and we are going to reduce the dimension to the required stage. What else? I will leave that. Usually the part transporter is going to be specialized with transportation of the bars. It's going to have a special shape, and we usually going to cut the part to the length in our factory. Something like we're going to use the same machine to pre-cut it. Leave it for the storage if required. Now it's very important to check the dimension of the part. We buy it at 60 millimeter. We need to check it. The problem is going to be if the bar diameter is going to be more than 60 millimeter, because this will affect the insert of the cutting tool depth. Because, for example, I'm going to insert it to 1 millimeter. The force is going to be calculated by the machine for 1 millimeter. But if the diameter of the shaft is going to be more than 60 millimeter, this will increase the depth, for example, by 2 millimeter, and this will break my cutting tool. So that's why we always need to check what the actual dimension we are going to have. Hardness test to check what will be the hardness for the shaft. Is it going to be compatible with the specification of the supplier or not? Usually when we do a continuous machining for the for on bar work, we need to use something called the bar feeding, where it's going to have multiple items at the back. We're going to feed it a little bit by little bit to the machine and do the machining on them. The driven shaft actually is going to have the same thing, and the cutting bar stock can be pre-cut before we're going to feed it to the machine. This will be machining shaft gear blank. You can see that this one actually is going to have the twin spindle. We said that twin spindle is going to be an optional. Usually you're going to do your work on the single spindle machine, and you have to do the changing of the size manually, or you can use two different machines. Each one is going to do the operation. For example, the first one is going to cut the first three stages, then the second one is going to cut the last stage. Cutting all the supply, we said we can do that by the port approach, or we can do it by the hopping operation, or even do it by the milling machine with the indexing tool and using the tool which is called the dovetail. So the cutting of the gear is going to be done by using the gear hopping, and the heat treatment is going to be required for the gear and the shaft. The grinding process is going to be followed to get the goods finishing. Also, grinding process is going to be done for the gear teeth to achieve the good surface quality. That's not the video. Okay. Yeah, this will be the grinding for the gear teeth. We described actually why we need to do that. Final inspection for the dimension and the surface finishing should be done before we're going to finalize the product. Okay, so do you have any questions before we're going to go forward? You can watch the video. I already had, from last week, I already have covered one of the reports. Take a look on them. We still have time for the due date. If you have any questions, just come back to me. I will upload this video to the general team. And so it's going to be available for all the students. And again, as I told you, that if you need any questions, just come back to me, and I'll be more than happy to answer your questions.